Let's get started with today's lecture. So remember, from the beginning of the class, right, Signals and Systems class, we've been saying our goal is to represent signals, right, as sums of sinusoids actually. And why is this important? Because you can think of these sinusoids as building blocks. Like, you have bricks, right, to build buildings in a way, and you put them on top of each other to form the basic structure of a building. This is similar. We decompose signals onto these basic building blocks. So later, with some given coefficients, we actually add these basic building blocks, which are the basis functions, to form a signal, guys. And the reason is those basis functions help us to represent a signal very compactly and to concentrate or focus on important parts of a signal, eliminate noise, for instance, or we can compress information by setting to zero some of the coefficients corresponding to some different basis terms. So we will, actually what we're doing is signal representation. This is what we're doing in a way. I mean, in general, this is general mathematics, signal representation in terms of basis functions. This is what we are talking about actually without you knowing it. Maybe I mentioned it because complex sinusoids and real sinusoids are our basis functions. And that transformation or representation is called a Fourier representation. So if it was discrete, I will start with actually a continuous time signal. We will start our Fourier series, but if it was discrete, we will come to this. This is our basis function. These are the coefficients. Okay, you see at signal time point n. You're right. I'm not sharing the screen. All right, guys, sorry. Share the desktop. Oh, not the desktop. I'll show you guys just a sec. I will share the tablet. I have to first connect it. Just a sec. Now should be fine. Thanks. Thanks, guys. Is it there? No. Just a second. Okay. Let me stop and start again. The cable was loose. I just realized. So I was saying we're doing signal representation in terms of basis functions, and important special case is these are orthogonal. Important special case, these phi k, and we will see what orthogonal means, are orthogonal basis functions. I mean, these are, let's say, basis functions. We said they are the basic building blocks to represent a signal. And when they are orthogonal, we say actually they obey something like this. We'll integrate. We will start with the continuous one, but still, let me write this. Orthogonal basis means the inner product of these two guys. We can show it by these brackets. When this is equivalent, their inner product is 0. This is conjugate. Remember the conjugate form. So in Fourier expansions, this will be, for instance, e to the j 2 pi over n k. And this is discrete Fourier basis, but I mean, this was just for generic representation. This could be any other basis, doesn't even have to be an orthogonal one. any other, this is for K, it's a set, it could be 1 to infinity or some finite number of them, any set of basis functions. Okay, so now, I mean, K1 to infinity, we said these are basis signals. Okay, Fourier series is discrete Fourier series, it's just a special case. Okay, so our goal is really to have a representation that results in a low dimensional embedding, we call it. This is meaning the signal, when it's decomposed on this set of basis functions, has a small number of AK. So goal is desirable thing, desirable goal, small number of AK coefficients. You see, AK are the coefficients that multiply these basis functions, and we sum them up, right? Small number of AK are non-zero. This is really the goal in signal decomposition, right? So this would be, for instance, the idea in compression. In filtering or feature extraction, we try to keep the AK that are useful to us. For instance, for this was compression. For filtering, what we do is different. We can say keep AK that contain the signal, or important parts contain the signal, important part of the signal, discard AK that contain noise, for instance. This is actually really, noise is any unwanted effect, actually, guys. Any unwanted features, let's say. We do filtering to get rid of any unwanted features. Remember now, our current machine learning, deep learning era, we are doing, in a way, some kind of filtering with our models, right? We are trying to map from high dimensional data to low dimensional spaces. So it's really, we are killing those features in the data, suppressing them, and just trying to come up with a signal or data representation that is meaningful for the given task. Okay, so you have to have a task in mind to design such features in a way. So now going back to the continuous time, now general theory of Fourier series, we typically, guys, like to start in continuous time because it's really, the math is much easier in continuous time. General theory, I mean, I know you guys are like, hey, we are computer engineers, we work in discrete time, but you should really have a good grasp of the math in continuous time. You will see it's much easier to first understand things, then go to the discrete time. Theory of Fourier series, let's say. Okay, so any periodic signal. Now currently it's periodic, later with Fourier transform, it's gonna be any signal. So this is important keyword now, any periodic signal, x of t, with fundamental frequency. Now this is the key term here. So when it's periodic, I know I can find a fundamental frequency. I hope you studied your previous lecture. Okay, so without a periodic signal, actually I can't really find a fundamental frequency, right? Fundamental frequency f0 can be, guys, this is important, can be written as a sum of, now this is also important, harmonically related sinusoidals. Harmonically, remember what are the harmonics? Related sinusoids. Here, this is important keyword. What were the harmonics? Remember, they are actually kf0 are the harmonic frequencies with k integer, of course. Okay, k integer. All right. So Fourier remember, or I think last time we were really talking about the fundamental frequency, harmonic frequencies. Now we will say a Fourier representation or synthesis of a signal is really not surprising to you. This is the equation. Let's say Fourier synthesis equation. Sorry. Later I will show some signals to you. This is x of t, sum k minus infinity to infinity, ak. Just remember the signal representation I just wrote to you. E to the j 2 pi k f0 t. The basis function, just see, it's the same. I mean, I wrote it in discrete, but it's the same idea. Basis function, phi k, psi k, or here this is the psi k, okay? This is the continuous version. I mean, it was psi k of n here. These are the coefficients, Fourier series coefficients. Fourier series coefficients. Okay, AK. These are the, we said, basis functions, and they are typically orthogonal, and here it is orthogonal for the Fourier series and Fourier transform. We will show now. You should know, for instance, as a computer engineering major, like whether, if I give you some basis functions, whether they are orthogonal or not, you should know how to show. Take the inner product, right? But here it's an inner product in an infinite dimensional space. In this continuous space, we will see. These are basis functions. These are really, guys, building blocks for reconstructing, let's say, building blocks for reconstructing x of t. Okay? So f0 is the fundamental frequency. This is important. Please pay attention. And k, f0 are the harmonics. This is also important. AK are the Fourier series coefficients. These are important parameter here to represent our signal. So now let's check these orthogonality and zero integral property. These are important for basics, basis functions. Let's now say, but also pay attention here in our, so let's maybe move to blue. In our basis function, note that the basis function here in this case, which is e to the j 2 pi k f0 t, you see k is the index. I mean, I have a set of basis functions, okay? K is that index. So let's make this small k. Index of the basis function. Also, you see ak then ties to it. That's the corresponding coefficient of that basis function. F0 is the fundamental frequency. You see, actually, guys, this is, or this signal, you guys know this signal. This is a complex sinusoid, right? So in Fourier series, complex sinusoid or complex exponential, I mean, you already know what I'm saying because we were adding signals, right? Until this point, this was the idea. Now we generalized it. We were adding sinusoids actually. And we were adding first sinusoids with the same frequency. Then we started adding sinusoids with fundamental frequency and its harmonics, right? Or we know spectrum representation where we show all the existing frequencies in a signal. So complex exponential or sinusoidal is, these are the basis functions for Fourier series, okay? So you see it's really showing us this equation here. Is what it says is really just give me the AKs and I know the basis functions of the Fourier series. Of course, I should know the fundamental frequency. Okay, F0, I can. So actually what it says is given AK for a signal. for a signal x of t. We will not see how to calculate that. And f0, the fundamental frequency for a certain signal, right? I mean, for a given signal. If f0 is fundamental frequency, I can reconstruct, guys. This means, this synthesis means actually, synthesis means synthesizing a signal, building a signal. I can reconstruct, you guys will do this, a signal, or the signal actually, because we're talking about it's for a certain signal. The signal x of t as follows. You guys will say, hey, I know I can write, because I know all the AKs. Some can be 0, okay? Some could be 0. I can just have a finite number of AK, almost 0 maybe. And I know the fundamental frequency, so I can really construct my basis functions here. This is known. F0 is known. You see K is just the index of the corresponding basis function. Okay? So always recall more general way is really sum k, ak, ck, x of t. This is the more general version. Okay. So now these basis functions, this is important, guys, for you to know. Later, maybe you will be working on signal processing, data science, data processing. You may come across different basis functions. For instance, wavelets are other kinds of basis functions. You may look at their properties. This is, of course, the specific basis function, Fourier basis, e to the j 2 pi k f0 t. These basis functions have this two properties. Has two properties, important ones. One is the zero integral property. Second is the orthogonality property. Zero integral, one, property one, let's say. Property one, guys, is what we call zero integral for this basis function. I mean, always pay attention, there is this index, right? So it's a family. We call it a family of basis functions. K vary from minus infinity to infinity. It could be, you could be just working with a finite number of them. Okay? Family of, so we could say actually family of, that's why we say family of basis functions. This index is varying from minus infinity to infinity, creating really an infinite set of basis functions when you vary k. And those actually are, you see, with each k, you get a different sinusoid oscillating at a different frequency. For instance, with k equals 1, I get a sinusoid that oscillates with f0 frequency. With k equals 10, I have another basis function that oscillates much more rapidly, that's 10 f0. That's the idea, guys. So with all these, so for k equals 1, for instance, we said e to the j 2 pi f0 t. I mean, it has two components, remember? The real, let's look at its real. For instance, I'm just making this up, of course, just, I mean, hypothetically, frequency f0, but for instance, k equals 5, it will be oscillating with k equals, with frequency k f0. In this case, I mean, this is the real part, let's say. I'm just looking at the real part. This would be really 5 times fast oscillating. So this is another cosine in the real component. I mean, k 10, of course, is really, you see, increasing frequencies, right? I mean, it's really much higher frequency. So zero integral property is really, as the name says, zero integral. This is basis function, right? Property of basis function. Let's say, so I need to integrate this. Let's see, in one period, let's say, integrate the basis functions in one period. So we know the period is t0, of course, right? Given ak f0, so we know 1 over f0 is t0, of course. This is the fundamental period of the signal. It's a periodic signal, period of x of t, okay? This is important also. So integrate the basis function in one period. It could be any period. It could be minus t0 over 2 to t0 over 2, 0 to t0. It could be t0 to t0, doesn't matter. This is my integral. Just bring it here, the basis function, the general form. Okay, do the math here. We know how to integrate an exponential. It's not difficult. We have to take e to the j, we have to take 2 pi, j 2 pi k, f0 is in the denominator, right? And e to the j 2 pi k f0 t, this should be integrated or evaluated at 0 to t0, okay? So let's see, I have for t0, let's keep this here, 0, t0, j, 2 pi k, f0 times t0, this is 1, of course, right? Then minus, I need to insert 0 here, that is 1. Guys, you see, this is e to the j 2 pi k. Okay? Yes, that's e to the j 2 pi k. So I have e to the j 2 pi k minus 1. Okay? So this e to the j 2 pi k is really 1, right? For any integer k, I know this. So you would be like, yes, great, I already showed it is 0, right? It's a 0 integral. It will, so this is really 0. But when k is 0, for any integer, this is okay, equal to 0, but we have a special case. For k equals 0, guys, let's just get rid of this, or just, yeah. For k equals 0, look at my integral. This is a special case, 0 to t0, e to the j, I mean, it is e to the 0, of course, but let's write 0 times f0 t dt. This is 1. You see, I have a non-zero integral only for k0. So this is actually then the result. Let's write this guy. Then this property, first property, says 0 to t0 vk of t dt, which is equal to really e to the j 2 pi k f0 t dt. This is equal to 0 for k not equal to 0, but it's equal to the period for k equals 0. Okay? So this is the first property. This of a basis function. So let's write this nicely. So now let's move to, so this was property 1. It's important to know this. Now orthogonality. This is the second property. Remember, this was property 1, 0 integral. Now let's write property 2, orthogonality of, these are called harmonic complex exponentials also.
Can I ask why?
Yes, of course.
Basis function is equal to 1 for every k integer k? What's
that? Why every basis function is what?
Can you go to the previous page?
Yes.
We said for any integer k, it's equal to 1, but why?
Yeah. This is, remember, on the complex, just go to the complex plane. That signal, that's a constant on the complex plane, actually. Just look at what it is. Remember, this is cosine 2 pi and sine. I mean, this is equal to, just use always Euler formula. It's a good question. Thanks, you ask. When you see a complex exponential, it may be hard to know what's going on. Just always think of the Euler formula. Remember, this was cosine 2 pi k minus, plus j sine 2 pi k, right? So there is a cosine 2 pi k on the real, and on the imaginary, of course, with whatever k is, it's gonna change, but now we will look at k's. Actually, they will, sine part is 0, by the way, right? Just integer, insert integer k. Yeah, actually, it's always coming back here. K0, it's 1. K equals 1, cosine 2 pi, I'm back here. Cosine, you see, right? 4 pi, I'm back on 1.
Yeah, it's because 2 pi is period of.
Exactly. 2 pi is period of this signal. Yes.
Yeah.
Yes. Good. Thanks. It's good you asked. Thank you. So, guys, this property is important because in a way we will be seeing, we will be taking an inner product. We will project our signal on top of this later. Just right. We will be taking an inner product with the complex conjugate of this basis function. That's an inner product, x of t, vk of t. We don't want it mainly, other than at k equals 0, we don't want it to introduce any integral mess in a way. That's why this is a desired property of basis functions. We want them typically to have zero integral. We will see the orthogonality now, and you will understand what I'm saying when I say I project my single signal on top of it. First, let's learn the properties. Orthogonality is also very important. So, orthogonality means take two basis functions, meaning two different indices, right? So, again, take the inner product. So maybe let's say VL for the, okay, second one, Vk of t times V sub L of t, but complex conjugate, that's an inner product in an infinite dimensional this function space. We will show, guys, this is 0 for k is not equal to L. Okay, so let's show this. Let's show this. So let's just take the integral again. I mean, the same inner product. Okay, this is gonna be L conjugate t dt. So insert my form of the Fourier basis. Remember, these v are the basis function. E to the j 2 pi k f0 t times now the e to the minus j, right? E to the minus j 2 pi L f0 t, because that's the conjugate, complex conjugate of e to the j 2 pi L f0 t. Now combine these into a single term. That's going to be e to the j 2 pi k minus L f0 t dt. Now these two are k and L are integers. K, L are integers. So this k minus L is also an integer, right? Integer. We just learned from property 1, guys. E to the j 2 pi m f0 t. M is an integer. What is this integral? Look at the top part of the slide. This is 0 for m is not equal to 0, and it's t0 for m equals 0. So that brings me to here. I can apply this same idea here. You see this inner product, okay, of my two complex sinusoidal harmonically related complex exponential basis functions. T is equal to, guys, when m equals 0 means when k equals L, actually. It's 0 when k equals L, but it's, right? Any questions, guys? When k not equal to L. Somebody open their microphone, guys. 0, I mean, when m is not 0, meaning when k is not equal to L, right? And it's T0 when m is 0, meaning k is equal to L. I mean, when it's the same basis function, meaning this case is really actually when I have VL squared, right? Or VK squared. Somebody, guys, open their mic. Yes. Yeah, let me see, guys, just a sec. Okay, yeah, let's continue recording. All right, yes, thanks, Alvin. So let's continue recording. We said this is an important result, guys. We see inner product or, yeah, actually, let's say inner product of these two basis functions, Vk and Vl is 0 when their indices are not equal. So now my point from here will be this, I mean, important thing. You can ask me, given x of t, how to find a k. So first of all, we did this. We did Fourier synthesis. This is done, but let's just repeat. Fourier synthesis was given ak and f0 for x of t. We write x of t, then as we synthesized it. This is the like the forward pass in a way, or forward way, right? Because we construct or synthesize x of t. Now, the important question is, of course, how to find ak. Because when given a signal, now question, given a signal x of t, how to find, my question is, how to find ak. How to find the Fourier series coefficients. This is called Fourier series analysis problem. The Fourier synthesis is much easier. We are given everything already. But now we want to, this is called Fourier analysis, by the way. This is Fourier analysis. You see, analyze is to deconstruct something into its components and to be able to find ak, that's what you're doing. So we will start with x of t to do that. So answer, start with, guys, x of t representation. K minus infinity to infinity, ak. We will try to leave ak alone in this mathematical manipulation. That's the goal. And we know orthogonality property that will help us. Now we multiply both sides. Let's choose another index. Yeah, let's choose the same index here. E to the minus JL. Remember here, for instance, I mean, it could be another index, but let's bring something like that. So it's gonna be really some k ak e to the j 2 pi k f0 t multiply by, we don't need a parentheses probably, e to the minus j 2 pi l f0 t. Okay, multiply both sides by the complex conjugate or of the basis function. So I need also to do that on the left hand side, to the minus j 2 pi l f0 t. Okay. Now integrate. Maybe I should say this as the next one, next line. Integrate in one period. That's important, guys. 0 to t0. Here also 0 to t0, x of t to the minus j 2 pi l f0 t dt. Now the same thing here, some k a k e to the j 2 pi k. We can keep these together, by the way. Okay, but let's maybe, I'm doing it the long way, 2 pi l f0 t dt. Now exchange these two guys. Okay. Due to the properties of these basis functions, okay, k 0 to t0, ak is out, you see. Ak is just depending on k, 0 to t0, e to the j 2 pi, k minus l, this is minus, remember, f0 t dt. And we know this integral is 0 when k is not equal to l. So this is really 0 when k is not equal to L, and it's equal to T0 when the two indices match. You see? So we're using both properties here. In the end, this would mean I would have 0 from multiplying AK for all K other than L. So I just have in the end, I'm left with AL. This is the only surviving term. Because it's only non-zero. AL times T0, of course. AL times T0. So let's try to write this in a nicer way. This was some K. Now this is, guys, giving me AL times T0. Only surviving term is AK, AL. So you see in the end, we ended up with this equation or statement. Now we will rearrange it. Take this T0 now to the other side, and we end up with the AK term or AL term. Just change the index. You see what is happening, right? Now we end up with, let's change to AK. I mean, because we're always, I mean, this is just a notation. Change the index to, it doesn't really matter. Maybe I should keep it L. Are you going to be confused or are you fine? If I write now 1 over T0, remember T0 was multiplying the right-hand side, now it's 1 over T0. It's an integral in one period. X of t is multiplied by, you see, complex conjugate of the 2 pi L f k. Now we change the index. K f0 t dt. This is really a projection of x of t, an inner product with vk of t. Okay? This is projection of our signal x of t signal onto basis functions vk. Okay? K minus infinity to, I mean, typically we take in real life as finite number, of course, but minus infinity, let's write nice. Okay, so this is what we call the formula for Fourier analysis or formula for finding Fourier series coefficients. So this is really Fourier analysis, sometimes also called Fourier analysis integral. Actually, it's how to calculate Fourier series coefficients equivalently. Okay, this is okay. Let's just rewrite it, guys. By the way, it can be just, maybe I can write it here like this. It can be any period interval. So this can be any one period interval. The integral limits, I mean. This is integral limits. Let's write it openly. This can be any one period interval. X of t e to the minus j 2 pi k f0 t dt. Okay? Fourier series, we know how to calculate Fourier series coefficients now. This is important because now you can do this analysis, or you know how this analysis is done, okay? So maybe we could do a simple example. Let's see, Fourier, what are the Fourier? So let's do an example, guys. For instance, example, what are the Fourier series coefficients? Consider the beat note. I hope you guys went over the notes, beat note. Last time, remember, we saw a demo. There were two frequencies. Normally, if it's 2 pi f, for instance, an ft plus, I mean, there could be some amplitude, but cosine 2 pi f plus delta ft This was, remember, turned into something in terms of cosine 2 pi ft times cosine 2 pi. Check the exact formulas. 2 pi delta f, of course, delta ft. Remember, I hope you guys checked the notes and did a, really a sanity check for those numbers. Remember, in the demo there was a 220 hertz, but it should, I mean, once you know this exact formula, guys, check the coefficients here. Currently, I didn't memorize it. There could be a 1/2 here if it was a, right? I will have something like this, but check this. So consider the beat note. This was just a note from last time. Check previous lecture. You can ask your assistants to consider the beat note x of t cosine 2 pi 100t times, you see, typically f was a large one. Remember, frequency delta f is a small perturbation like frequency. So this is, let's say, 2 pi 10t. Okay, so we know this is really, let me see, actually, guys, this was a/2, this was a/2. I think now when I look at my notes, this is a, right? Now f is 100, delta f is 10. I need here 1/2 cosine 2 pi 100t plus 1/2 cosine 2 pi 10t, right? 110 f plus. Guys, we have to really check these because I have, again, this should be f plus 10, f minus, okay, f minus delta t. Now I got my mistake again, f minus delta t. And this is f plus delta t. Okay, so let's make this delta just for f plus delta t. This is, should be also delta plus. Now you see what I'm writing, delta ft, let's write it delta t. Okay, so now this will be 110, we will, and 90. 110t and 90t. Okay, now we should be fine. Please check your notes. We should be fine with this. Yes, Çağlar, yes, we are fine. I think 220, please check, and you guys do the sanity check for that demo. I don't know if we shared the link with you. Yusuf, Fırat, if you guys are here, I actually last time said, please check and correct it if it's wrong in the notes, or I think you guys probably checked it, and let the class know if there is a problem. Okay, correct. The notes should be correct. 11090, that's it, guys. So I want to ask you now, this is good. You see closer frequencies are added, large and small frequencies are multiplied. That's the idea. Okay, so we must add them and subtract them. Okay, so now, guys, what is the fundamental frequency? I can ask you, or my question to you are, what are the, before that, what are, I mean, my final question, ultimate question, what are the fundamental frequencies? Or frequency, what are, not what are, harmonics. I was thinking of the harmonics. What is the fundamental frequency and what are the harmonic frequencies, of course, then. Fundamental frequency of x of t. Do you guys have an idea? Two frequencies in the signal are f1 is 110 hertz, f2 is 90 hertz. So you need to find the greatest common divisor. Probably you guys got it right. 10. Yes, thank you, guys. Of those two, f1 and f2 are, then my fundamental frequency is 10 hertz. Great. We need this, right? The ultimate question was actually, maybe I should, this was the first question, but ultimate question is What are Fourier series coefficients? What are Fourier series coefficients of x of t? Meaning AK, because once AK, I know Fourier series representation of the signal. Yes, I was going to ask which harmonics are there. Some of you answered. So actually, we have 9th and 11th harmonics, right? 9th and 11th harmonics. So I have really exist in x of t. So I really have, like you guys said, but it says two-sided spectrum. Remember, A9, A minus 9, A11, A minus 11, right? I find them. Actually, because this is a cosine, I know how to find them easily. Let's just write. By the way, maybe let's also write why we have these. We have k times these guys, right? So I have really k f0, 9 f0 plus minus, and I have plus minus 11. Should be a nice 9. Oh. 9 f0 plus minus 11 f0, right? These are the 9th and 11th harmonics in the signal. Now we need to find 8th. Normally we use this Fourier analysis integral, but for a cosine and sine signal, guys, it is just simple to read it, right? Please don't go to the integral for sinusoids, okay? Yes, Sally, harmonics. So, are you fine? Are you guys, everybody, are you clear what is the fundamental frequency? Like, I mean, Y10 is the fundamental, 10 hertz is the fundamental frequency. Are you guys clear? I hope everybody in the class is clear with this. So then we went to the signal and we saw what are the frequencies in this signal, because this is a cosine signal and sine the same. It's easy to spot the frequencies in the signal. I mean, I just saw two frequencies. This signal x of t has two frequencies, which are 110 and 9. And we can see actually they are 9 times f0 and 11 times f0. That's why. Guys, so these are really, this is also plus minus, plus minus. This is really 90, right? Plus minus 90. This is plus minus 110 hertz. That's why we said, this is very important to understand. These harmonics, like 9th and 11th harmonics, and it's a real signal, cosine signal. So I know actually I have plus minus both frequencies. Is it clear? Sorry. Now I'm asking you, what are these? A9. What is A9? What is A minus 9? A11, A minus 11. What are these? Normally, yeah, one of them is sine. The same thing. Only coefficients will change. Okay? So I can just maybe let you guys tell me what these are, and I will write that here also. What are A9 and A minus 9? Guys, remember the Euler formula? I'm asking everybody in the class, what is A9? What is A minus 9? What is A11? What is A minus 11? Guys, can you think of this? Then we will give a break. Actually, this is the example before the break. Okay, you just learned it. Maybe it's a little bit looking difficult, but expand x of t with Euler formula. Rewrite x of t. I know cosine is, you should know Euler, guys, Euler formula. You see, it's really helping use Euler formula. 1 over 2 Inverse, this is the inverse Euler, of course. But I mean, I'm saying Euler just to mean either forward or inverse formulas. 1 over 2 times 1 over 2, so it's really 1 over 4. And this is inverse. 1 over 4, the complex exponentials. I'm trying to bring things to this kf0 e to the j 2 pi kf0 t form. 2 pi k, or actually it's 110 t, right? Plus 1 over 4 e to the minus j2 pi minus, this is minus 110 actually. So maybe I can write j2 pi minus 110 t, the same with 1 over 4 e to the j2 pi 90 t. These are important, right? And plus 1 over 4 e to the j 2 pi minus 90 t, and these are actually kf0. So this is real 9 times 10, minus 9 times 10. You see what I'm writing, right? This is really 11 times. Maybe I should have written it exactly like that from the beginning. It may be easier to understand. 2 pi 11 times 10 times t. This is f0. This is k. It's 1 over 3 e to the j 2 pi minus 11 times 10 times t. Again, f0 and k. You guys see it now, right? And we did the same here already. So now you guys answer from here. You guys answer what are A9, A minus 9, A11 and A minus 11. I'm waiting for an answer. What we're doing is not really that I could say complicated. We're taking a signal like this. It's a sum of sinusoids. You were already doing it before. We will plot the spectrum actually. We will find its spectrum representation, meaning we want to show and display the frequency content. But here I'm also asking you, coefficients are also important in terms of the basis functions, which are really what I already drew or noted here. These are the basis functions, remember? Now I think you can probably, yes, exactly, it's 1 over 4, not minus. Just 1 over 4 because the frequency is getting multiplied by minus k, okay, not the coefficients. So this is really all 1 over 4, 1 over 4. So if I had sine, for instance, in one, we can do it. Let's maybe just first draw this, plot this, and then do sine version. So it's spectrum representation then. You see, we've been doing this, but now for periodic signals, we call it a Fourier series representation. So in graphical form, it's really here frequency f. Maybe, yeah, let's keep it frequency f hertz because we've been talking about that. And let's just bring them to 90 and maybe 1110, 90, and maybe actually let's draw them a little bit closer. 1110 minus 1110, and it's really just the same 1 over 4. So this was A9, this is A11, this is A minus 9, which is 1 over 4, okay? And this is A minus 11, which is again 1 over 4. This is the spectrum representation of x of t, okay? So you see now we display the Fourier series coefficients. We say, I mean, these phasor complex coefficients are really the Fourier series coefficients. So you guys ask, what if one of them was a sine? So if, for instance, x of t was really, I mean, let's maybe just make it 3 sine 2 pi 5 t, and you can have another component, it's fine, but now it's only really writing this as 3 e to the, remember, or let's keep the original so you guys can remember the Euler formula 3 over 2j, remember it's 1 over 2j, e to the j 2 pi 5t minus e to the minus j 2 pi 5 minus 2 pi 5t. Remember, this was the sine formula. Now you see in this case, my coefficients, I mean, here it's just one single sinusoid, so my f0 is also the fundamental frequency. It's really just 5 hertz. So I have really A1 and A minus 1. Okay? So what are the Fourier? So exercise. What are the Fourier series coefficients? Question. Coefficients of x of t. What are AK? You guys would be like, hey, I just have a fundamental frequency that is actually k equals plus minus 1, right? For this, I mean, sine. So this is really kf0, which is k equals 1. I mean, 1f0, 1f0. And this is really actually minus. So from here, I know I have minus 1 times f0, right? So this minus comes here. Kf0. So I have then A1 here is, it should be complex conjugates. We know actually, I will derive after the break. So A1 is really 3 over 2j, which is 3 over 2 e to the minus j pi over 2. A minus 1 is, this time I have a minus 3 over 2j, but you should always write this in phasor form, not leave it as it is, phasor form. So remember, minus 1 is e to the j pi. And I already know actually it's the complex conjugate, but e to the j pi minus e to the j pi over 2. This is the a minus 1 term. And you can, again, just play the plot the spectrum. F is hertz. 5 hertz minus 5 hertz. I have the a case. I mean, sometimes we also say this is k equals 1. Okay, the same thing for here. I could have written it actually. You guys can say this is k equals 9, this is k equals 11, k equals, okay, minus 9, k equals minus 11. Okay, this is important. Because sometimes we show it by k and just show it as discrete k, 1, 2. Because once we know f0, of course, we know the fundamental frequency. So k, f0 are really what are coming here. So these are now in the spectrum representation, really 3 over 2 e to the minus j pi over 2. This is A1. This is 3 over 2 e to the j pi over 2. And you see these are really complex conjugates. We will show for real signals, Fourier series of plus minus k are complex conjugates of each other. This was the same here, guys. These are also complex conjugates of each other. But they are real, so we didn't really realize. Okay? But for a real signal, I have to really note this. For a real signal, we will drive it next. For a real signal, not a complex signal, I mean. Any questions? We are over the suggested time frame or time duration for the lecture. They were suggesting max 40 minutes. We are 1 hour, more than an hour, but it's fine. Any questions? Because we really covered the most important parts of the Fourier series. We will have a little bit more, but still. Any questions? Okay, when deriving the signal from the graph, yes, Arda? Yes, they are really exactly. Yes, get everything in cosine form and phase shifted. Good question. Remember, cosine, you shift it by pi over 2, right? Phase shift. Exactly, and it's a sine. Exactly. I agree. Always get it in the, I would also do the same. Do you see what Arda is asking? Very good point, guys. reading of the signal from the spectrum. Okay, so for instance, there will be k equals 2. Let's say I don't need to always have the first fundamental form or first harmonic. K is -2. Maybe let's say I have k equals 5 component, and it's a symmetric spectrum. So I know it's a real signal, and I can represent it in terms of cosines and sines. What Arda is saying is a good point. Read it off like these are A2. You can read off these phasor plus phasor coefficients. From here, write a cosine. So I would say, for instance, given spectrum, you guys should be able to do this. Write down the signal. Signal x of t. Just bring here, because I know from Euler formula, I will have, these were the 1/2s, 2a2. We will be doing this, but okay, cosine 2 pi. This is 2 hertz, we said, right? K2. Okay, k equals 2 f0t. I know this is there, and I have 2a5 cosine 2 pi 5 f0t. Very good point. If, for instance, you want a sine signal, always from here you can say 2a2 sine 2 pi f0t minus pi over 2. You can always add those guys. Right, minus pi over 2, add the phase shift. Okay, this is equivalent. And of course, whatever these coefficients are, you have to just affect them. And also, if there were some e to the j parts, guys, here in the A2s, they will be here too, right? So that's gonna come. Don't worry, I will do it after the break. But for this simple case, let's say they were real, I can easily write it like this. Okay, so let's give a break now and meet up. Let's continue with where we left. So I think there was a good question at the last point before the break, guys. So what is A0, by the way? Fourier series synthesis or Fourier series analysis equations. We said, remember, AK can be found by, this is just a scale, 1/T0, integrating our inner product of the signal with the basis function, but it's just complex conjugate or Hermitian, we call this, 2 pi k f0t. We should know the fundamental frequency, of course. This is very important, dt. When k is 0, you see this really reduces to A0 is the area underneath the signal in one period, but also normalized by 1/T0, scaled by T0. 1/T0, let's say, xt, because this will be to the J0, which is 1. I have really, you see the 0, A0 Fourier series coefficients is really the integral. This is the integral under, or area under the curve, or under the signal, let's say, the signal x of t in one period. Because it's repeating itself, it doesn't matter, right, which period it is. And of course, scaled by T0, okay? This is something we should probably note too. So A0, you see, can be really found easily by looking at the form of the signal, okay? The area under the signal. So now we want to also do a special case, a little bit more math, for a real signal. We hinted at it a little bit. For a real signal, guys, not complex, meaning not complex. All the cosine signs we've been talking about, not the complex exponential, they are real signals. And periodic signal, of course, and periodic signal, and of course periodic, we can calculate a property of the Fourier series coefficient. So AKs have a, let's say, AKs have a special property. We will see now. To derive it, let's see, let's derive it. Okay, let's start with x of t representation again, as we did earlier. Remember, this is really k minus infinity to infinity ak e to the j. I mean, the Fourier series coefficients times the Fourier series basis, right? Now, for a real signal, I know its complex conjugate is itself. So take the complex conjugates on both sides of this equation. Okay. Now let's continue. This is really equal to x of t, right? Itself, it's real. Because x of t is real. Now continue on the right-hand side, k minus infinity to infinity, because conjugates, complex conjugate just affects, of course, the complex parts, I mean, which are ak and, of course, e to the j 2 pi k f0t. So I will have a ak conjugate, or maybe I don't need parentheses, k conjugate e to the minus j 2 pi k f0t, right? I hope this is clear, guys. Minus. Now, this is my, okay, x of t e to the minus j. Okay, great. So now, let's also, guys, in the original one, let's do, okay, from here actually, let's do a change of variables. Change of variables, okay. Let's say k prime is minus k, because some will not be affected, right? Right? I mean, when I make k minus k, because I'm summing minus infinity to infinity, this should not be a problem. So this I'm continuing from the above here part here. This x of t is, now let's continue with k prime. Okay. Again, minus infinity to infinity, but it's fine. It's the same because it's a sum. Now, a conjugate minus k prime, okay, change of variables, do it on this equation, because I'm trying to get rid of this minus k in the basis function. That's the idea. E to the j 2 pi k prime. I mean, I could have done it m or l, whatever other index you would want, but k prime f0t, okay? So you see, actually, I have, look at this original equation and this equation, we just derived actually because they are equal. AK is equal to A minus K. I mean, K prime really doesn't matter here. They are equivalent. We just derived this for a real periodic signal, meaning for a real periodic signal, guys, the Fourier series coefficients, the negative, or I can rewrite equivalently, just put the minus k, again do a change of variables. It's really saying to me that the negative frequency, think of the spectrum representation, okay? The negative frequency components are really complex conjugates of the positive frequency component coefficients. And we've been seeing this actually time and time again, because we've been working with real sinusoids. This is an important property, guys. So, okay. I mean, I hope you understand what I did here, right? We really said, because x of t is also equal to k prime ak. I mean, k prime or k doesn't matter, but let me rewrite it just for your notes. This is really the Fourier series representation of x of t. And then we really equated these two terms, okay? I mean, that's, or K prime, then I just switched it to K just to get rid of it, okay? So maybe let's not bring it and confuse you. I think this is fine. Is this clear? This is a nice result we typically use. Now, actually using this, we will write this time. Now, using this result, I mean this result, A minus K is a K conjugate. Guys, we will derive an equivalent Fourier series representation or synthesis equation in a way using real sinusoid basis, not the complex sinusoid basis, okay? So those will be cosine 2 pi k f0 t, okay? So you see, but for real, always pay attention. This is valid only for real sinusoid signals. Let's go to now our real, say x of t is real. Okay, so again, start with the general k, like say, general Fourier synthesis equation, k f0 t, okay? Now for x of t real, okay? Real signal. Even before the real actually assumption, let me not confuse you. I will use all Euler formula to open or expand this up. Use Euler, then use the real signal to look at the plus minus k coefficients. Use Euler formula. You guys know it very well. So x of t, k, okay, k minus infinity to infinity. I can maybe just, this was really k minus infinity to infinity. So it's really coming from minus infinity to some place. So let's start with some minus n e to the minus j 2 pi and f0 t, okay? And guys, I'm really skipping some terms. A minus 2 e to let's go to the second harmonic. So nth harmonic, capital nth harmonic I wrote. Now I'm writing the second harmonic, minus 2 f0. This is minus 2 f0 t, of course. Okay, a minus 1 e to the minus j 2 pi f0 t, the first harmonic term in the negative frequencies. Now go to, of course, there is a plus a0. Now go to the plus versions of these guys. Just on purpose, I will write them like, you know, and here I will write, let's say a1, the plus 1, 2 pi f0 t, plus a2 e to the j 2 pi f0 t. Of course, there will be these guys, a n e to the plus j 2 pi n, and then here we should have all the others to infinitely many terms, right? But let's just concentrate or just look at the finite number of them because it will carry over to all the terms, of course. Now, for a real signal, now we use that actually, real. So let's say real signal. For real x of t, guys, what we know is this a1 or a minus 1 is equal to a1 conjugate. A minus 2 is a2 conjugate, right? And this guy is a sub n conjugate. That is great because then we combine these a1 and a1 conjugate together. Let's maybe make them with square brackets so we see what we are doing. We combine these two guys because then I can use my inverse Euler formula to go to the cosines, right? That is the idea, exact idea, guys. So now I have x of t equals a0 is itself. because it doesn't have any symmetric terms. It's in the middle. And then I will have join these an and an conjugates into 2 cosine. Use inverse Euler formula. 2 is in the parentheses a1 cosine 2 pi n f0t. Okay, let's just, yes, this is a big parentheses. Let's make then n. Okay, a1. Okay, let's start with a1. Size f0t. Let's start with a1, a2 cosine 2 pi 2 f0t, right? This is important here. Then go all the way to a sub capital N cosine 2 pi the capital Nth or nth harmonic and f0t and plus other terms, of course, infinitely many, but we get the point, I think, right? So now I can really write x of t. Again, let's leave a0 aside, okay? A0, 2, okay, let's leave 2 here and write this as an infinitely many sum. A minus infinity to infinity, ak cosine 2 pi k f0t. Okay, here, this is important, you see. I think a0, no, it doesn't go in because it doesn't have the 2. Then we could just relabel a0 as this 2 a0. It would be the same thing, but it's fine. Okay, so if we had phase, guys, by the way, I noted this for you. We could always have phase, of course, in this, a phase shift. I mean, it's the same formula, but with a phase. I mean, nothing changes really. So let's join this 2 into this AK. Remember, we have, by the way, you guys did not warn me. This should be really from 1, right? Because I have already combined. Guys, this is important. I have already combined plus minus case together. So now you see, this is important actually. Let's maybe take it into a rectangle. Into a box, I mean. All right. So this is really the another representation. I mean, or again, this is Fourier series representation for a real signal. But you can also stick to the original one. It doesn't matter. No problem. They are equivalent. Equivalent to the previous one. But uses a real basis. This, right? This is the real basis. Okay, that's good. By the way, I think this cosine probably should have a larger parentheses. And let's make this a little bit smaller. Okay, I think this is fine. Okay, so now I was just saying I can also combine this 2 into AK and just maybe have here an AK cosine 2 pi k f0t. If I had a phase, it would come here, guys. If we had phase, I mean, it's really not changing too much. It's coming as a phase shift. Fourier series coefficients from here, Fourier, but however, should be, we should write this. Okay, it's a little bit cramped here, but they will be, you guys can see, AK over 2 e to the j phi k. This is little ak. And similarly, a minus k is a minus k over 2 e to the actual phi minus k. It's minus j phi k. It is actually, yeah, the same, because I'm reading off from the cosine. Let's not write minus k, actually. It's the same guy, of course, because it's cosine. AK, I mean, it's really the same AK over 2 e to the minus j phi k, because I know it's really the complex conjugates of each other, right? This AK and minus AK. Is this clear? Until here, what we did, we after the break, we just said, let's rewrite this representation for a real signal, because it may also use a real basis function like these cosine 2 pi k f0 t family of functions. And we should know how to go back and forth between the Fourier series coefficients as we did here. Okay. And the representation in this synthesis, real signal synthesis equation. Okay. So I think we can do a few more examples. Let me see. Yeah, maybe this is a good example. Yeah, let's do this. Any questions until here, please ask. Of course, anytime, guys. So let me give you another signal, and sine cube 3 pi t. And my question is, find the Fourier series representation. So that would mean actually find the Fourier series coefficients, okay? If I ask you find the Fourier series representation, meaning equivalently coefficients. Because once I know AK, then I can show the spectrum of x of t very easily. You see, from the first day, probably we've been talking about frequency spectrum of signals. It's a very important concept because all signals, all data have frequency constant. How would you go doing this, or how would you go about this problem, guys? Any question, any thoughts? Not questions, but I'm asking the question. Any thoughts on this? Remember, when you see sine cube, I mean, you should just directly think of Euler formula, because the question, of course, relates to the question, but if we are talking about Fourier series coefficients, we know those basis functions are complex exponentials, and if I can actually convert this signal when it's a sine cosine type signal, or it involves complex exponentials, it's very easy to find Fourier series coefficients. Why? Because once I can expand this into its complex exponential form through Euler formula, I all directly have the Fourier series coefficients. That's the idea, okay? So let's now write this, x of t. What is the sine 3 pi t? And to do that also, you need, when I ask you Fourier series coefficients, you should ask yourself, what is the fundamental frequency? You have to find fundamental frequency of the signal, because otherwise you can't write the basis functions. Because with F0, we know the basis functions, right? We can express the basis function form. The complex exponential basis, which is harmonic complex exponential basis, of course. Harmonic comes from KF0, right? That's important. Complex exponential basis. So let's use, you have to then answer, you have to expand with Euler formula. I mean, inverse Euler or Euler, you know which one to use. Of course, this is inverse Euler, 1 over 2j sine 3 pi t e to the j 3 pi t minus e to the minus j 3 pi t. We have to have the cube of this guy. So I need to really have 1 over 8j cubed is minus j. Okay. And I need to open. Let me just use this cubed formula. We have to recall here, guys. A minus b cubed is really a cubed minus 3a square b plus 3ab square. Remember, minus b cube. I'm gonna just effect or use this formula here now. E to the j 9 pi t, right? Let's do it together. Minus 3a square e to the j 6 pi t times e to the minus j 3 pi t, now minus plus 3a b square. And minus e to the minus j 9 pi t. Okay? It's clear, right? Now just rearrange the terms with the minus j is a j. I know it's a j, or I can rewrite it as e to the j pi over 2 in the numerator over 8. Remember, that's a phasor form we are used to. 1 over 8 times e to the j pi over 2. I have e to the j 9 pi t, 3 j 3 pi t. So think of the fundamental frequency. Okay, what is the fundamental frequency? We are after that to be able to write the Fourier series coefficients, because those AKs are really at multiples of F0. And we have to know which harmonics exist in this signal. Okay, e to the minus j 3 pi t minus e to the minus j 9 pi t. Now, what is F0? You guys can answer, please. Should I write it a little bit nicer? What is the fundamental frequency? Probably you guys got it. I mean, it's obvious, I guess, here. I mean, from here, it's 3 pi radians. And over 2 pi is 1.5 hertz. Yes, good, guys. Salih, be careful. It's not 3. You see, 3 pi is the radian frequency, remember. So from here, guys, let's write it. Omega 0, fundamental radian frequency, remember, is 3 pi radians per second. Then F0 is really 3 pi over 2 pi, which is 1.5 hertz. Good. So you see, which harmonics do I have in this signal then? Yes, thanks Arda, thanks Yusuf. First and third, great, perfect. So guys, we have, let's say, e to the j, yes, let's write it here. First and third harmonics exist. And that would mean you guys would say, I have A1, right? And I have A minus 1, because it's a real signal, right? Real signal. You should note that. These will be complex conjugates of each other. You also know that, and we will see. And I have A 3 and A minus 3. Oh, sorry, guys. Oh, okay, we will find this. Sorry, all right. All right, A minus 3. So let's write those, guys. Yeah, actually, maybe let's even write them here. Sorry, guys. Here, let's say A1, A plus minus 1. We have A plus minus 1, A plus minus 3. We noted here. Let's write them here. A1. What is A1? You guys just find the corresponding term. This is that basis, right? E to the j 2 pi 1 times f0 t is that term. So I have really minus 3 over 8 e to the j pi over 2, but I don't like minuses there. So that's an e to the j pi for me. So it will be, it's maybe for your notes first write the full thing, but then minus 1 is e to the j pi. So I have really e to the, I could have kept it as e to the minus j pi. I guess I did it in that way. Yeah. Guys, let me then write it, because I know can write minus 1 as either e to the j pi or e to the minus j pi. to the minus j pi e to the j pi over 2 times 3 over 8. So really this is 3 over 8 e to the minus j pi over 2. You can check a minus 1 from the equation how to extract it, but I know from here a minus 1 is already, because it's a real signal, the complex conjugate e to the j pi over 2. Okay? You guys should know or understand this easily. Now A3, let's read of A3. That's okay. First of all, 1 over 8 e to the j pi over 2, right? From there, actually, a minus 3 is easy, which is 1 over 8 e to the minus j pi over 2. Now, the spectrum is really, let's keep it on the same page. I can write here f in hertz, or I can also write this as the k, or which harmonic is there type illustration. Let's make it 0 and let's bring it to, so actually 1.5 and 4.5, right? Or let's, yeah, okay, it's fine. Okay, so let's write the equations here, A1. So this is really k equals 1, k equals 3, k equals minus 1, k equals minus 3. Let's bring the terms here, or the coefficient, I mean. A1 was 3 over 8 e to the minus j pi over 2. This was A1. So this is really A minus 1. You guys can see, write it down. And this is A3, which is 1 over 8 e to the j pi over 2. And this is really a minus 3, which is 1 over 8 e to the minus j pi over 2. Is this good? Yes, are we following? So this is this spectrum of x of t. So if you were actually asked about the Fourier series coefficients of this signal, you would be like saying AKs are 0 for k not equal to 1 minus 1, 3 minus 3. And then you should write the terms here, like exactly 3 over 8 e to the j. It was pi, minus pi over 2 for the k equals 1. 3 over 8 e to the j pi over 2. You can just write it in a compact way like this. E to the j plus minus pi over 2 for k equals minus plus 1. Because then I know it's really for minus, it's plus pi over 2. The same thing for these guys, e to the j plus minus, right? Guys, this time it's plus for the A3, 1 over 8. Okay, this was 1 over 8. Plus minus 3. Okay, so these are the Fourier series coefficients of x of t. I think we have some drawings, nice drawings. I can show you those actually. Now, guys, any questions? I will go to some slides. I think quite straightforward, right? It will look a little bit more difficult when we go to, maybe let's do it also on the tablet and then go to the slides, guys. Okay, so this was an example signal already in sinusoid form, in sine form, let's say, right? Because it was really x of t sine cube 3 pi t. Now next, let's just give a waveform of the signal. Okay, let's just work on a signal with a signal with a given waveform. Let's say, for instance, square wave, given waveform. So let's do it in the next page just for clarity. So given x of t is the square waveform, is the special square. I mean, you can have it in different, and it should be periodic, of course, is the periodic square waveform. You have to calculate, I'm asking you, calculate Fourier series coefficients of this guy, okay? Coefficients of x of t, okay? So, guys, this is, now I'm giving it even just in a plot actually. Let's say this is my x of t in time domain. It's a periodic signal. This was 0.02, and it repeats itself, of course, because it's periodic t. So, okay, so 0, 0.04, 0.06, etc. So minus 0.02, minus 0.04. Okay, I think makes the point. Let's make the amplitude 1. This is obviously a periodic signal. So I can really talk about its Fourier series coefficients, right? AK. We are after AK. You see, this looks a little bit more difficult. Now we resort to our analysis equation. Where was it? Guys, we did a lot of example here. We project that signal, guys, because we know its form actually. Even if it's given as a plot, actually we can write it mathematically in one period. And I need to do this integration or projection of that signal onto the basis function in one period. So we have to, first of all, again, define or find the fundamental period and the fundamental frequency, because it's given in the time as a time waveform. First, find the period of the signal. And we will make use of this integral. Of course, it can go from 0 to t0, wherever we find it more convenient. It's fine, okay? So let's just do this. First of all, what is the period? So you have to ask yourself, because from there you go to fundamental frequency. For instance, I mean, I can just find this interval, right? So this would be my t0, I guess. I mean, I already said it. I was going to ask this, but I just find a repetition interval, 0.04 seconds. This is good, right? This is clear for everybody. So we say t0 is 0.04 seconds. From here, f0 is 1 over t0, which is just 25 hertz. Okay? Now it's great. I know the fundamental frequency. I know the form of my e to the j 2 pi k 25, right? T. These are then the basis functions, family of basis functions for that I should be using, right? To decompose my signal onto, project my signal onto, project my signal onto this basis function set. Okay, so now let's use our good old Fourier series analysis integral, which is ak 1 over t0. Okay, let's first write the equation without the numbers. 0 to t0, I need to, this is one period, 0 to 0.4, for instance, 0.04. Let's use that, for instance. X of t, you see, is being projected onto e to the minus j 2 pi k f0 t dt, okay? And also remember, a0 is easy to find, 1 over t0, 0 to t0, x of t dt. It's just the area, remember? So you can always look at or look for a0 first. T0 I know, 1 over 0, 4. The area underneath one period is, what is it? 0.02, right? So I really have A0 equals 1 over 2. This is a given. This is great. So this is K equals 0 is already handled. Now, by the way, I can also express x of t in one period of the signal in mathematically, right? Express it mathematically, meaning it's really 1 for t between 0 and 0.2 or 2, and it's 0 bit for the other remaining part of the 0.02. Okay, I should just be here. 0.02 t 0.04, let's say. Okay. So this is one way to write, I mean, express by my signal mathematically. Express x of t mathematically by looking at the graph, right? Are we following until here? So far, so good, right? I just gave you a signal and I said you can easily calculate A0. You have to find, it's a periodic signal because we are after Fourier series representation. Then we calculated A0 and F0, of course. First T0, fundamental period, then F0, fundamental frequency, A0. You can just check now. Let's look at other AKs. Okay, AK, then let's continue with AK, guys. So AK, 1 over T0, let's write, it was 0.04. Let me quickly write this. The ideal equation is I replaced T0 with 0.04. X of T. In that period, we will, of course, now insert X of T, 2 pi K, 25 T, dt, right? I inserted F0 also. So this guy will be 1 over 0.04. Now I have two parts of the integral. 0 to 0.02, I have signal value is 1. E to the minus j2 pi k 25t dt, and plus 0.02 to 0.04, 0, right? The signal is 0 in this interval. So I really don't get anything from the second part of the signal, which is good. So this really goes to 0. Just do the math for the first part. I know how to take its integral, so let's just, guys, do it quickly here. We have 1 over 0.04. It was 25 already. We know that is F0 because e to the minus j, let's do the integral, minus j2 pi k 25t over minus j2 pi k 25, right? And we need to evaluate this from 0 to 0.02. We are all clear, right? This is really high school math, probably. I mean, integration, if it's still in the curriculum. I mean, or at least, let's just say, calculus, freshman year calculus. Guys, because sometimes students are upset that I'm saying this is high school math. Don't be upset. It's at least your freshman year calculus, and I know all of you have already passed those courses. So e to the minus j 2 pi k 25 times 0.02 minus 1, right? E to the j 0. Everything becomes 0 when I insert t equals 0 over minus j 2 pi k 25. Guys, that's the minus 1. Now do the math. This minus, let's take it up. So I have 1 because this is equal to, this term is equal to 1. 1 minus, because I'll just keep j 2 pi k 20. 25 cancels with the scale 21, guys. There was a scale at the beginning. So this guy cancels with this. So I have j2 pi k in the denominator. 1 minus e to the minus minus j2 pi k 25. Okay. I didn't multiply these two. When multiplied together, they are 1. guys. Okay, they are 0.2, sorry. 2, okay, and there is 2 also. Okay. Okay, my cat is here, so Yumi, please go away. All right, guys, just a sec. I have to take him out. He wants to play. Just a sec, guys. Yes. All right. No, actually, I stopped the recording because my cat arrived, and now we continue. Guys, here I was saying, actually, just do the math here. Do the multiplication. 2 times 25 is 50. I'm just looking at this term on the previous equation to the last one. That's all of them together, actually 50 times 0.02 makes 1. So this term is really, becomes minus j pi k. Okay? So we have this term. We end up with this guy. So let's go to the next page. I think you guys can do this. I mean, really, this may look difficult, but it's really just mathematical manipulation. Guys, don't really, it's not difficult at all. So, sorry, let's not do this. Okay, I will delete this page. Okay, let's continue with this page and we can add more if needed. Okay, so now we have to notice e to the minus j pi k is really e to the minus j pi to the power k, right? We're looking to simplify this last term, okay? That's what we want. Now that is e to the minus j pi is minus 1, right? Always think of the complex plane when you see these things. Minus pi, I go by pi to the real line on the negative side. So minus 1 to the k. So this will bring us something, some distinction between odd and even case, right? Now that's what we want, because this is really 1 for k even, minus 1 for k odd. So now a case then will be the whole, you have to summarize these. We already found a0 equals 1 over 2. Look here. Okay, middle on the right. So let's write this guy. Okay, 1 over 2 for, we should say k equals 0. So when k is even, okay, let me bring the final equation here. Guys, final equation we got was ak is equal to 1 over j 2 pi k 1 minus e to the minus j pi k, or which is really equal to, now you guys can write it as minus 1 to the power k. So when k is odd, that's a minus 1. When k is even, that's a plus 1. Okay, it is 0 when k is even, right? So this is 0 when k's are even. For all k's, you see minus infinity to infinity, all integers. And then it should be just 2. This is 2 for k equals odd. So, and it is 0 for k is even. So it's really 1 over j pi k. And this is also, guys, equal to, okay, let me write it as k odd. And this guy is equal to e to the minus j pi over 2 over pi k, right? So this is, this helps us to draw or plot a spectrum. I think this is in the slides, but let me do this just for the completeness of our notes, lecture notes. Any questions, guys? No, Salih, when k equals 0, a0 meaning, right? The coefficient 0, Fourier series coefficients, that's the area underneath the signal, right? We derived it, it's here. I mean, we derived it in the previous slides, but this is my a0, and we just calculated this integral in one period, but it has to be scaled by 1 over t0, just be careful. Then it ended up being 1 over 2. It's not 0. Yeah, there are other signals when actually it will be 0. We will see. I will show some examples. You guys will be working this mathematically. This is really, don't be scared at all. Very straightforward mathematics, guys. No tricks. You just have to start somewhere and know the definitions, I mean, and continue. So, okay, 1/2, let's say, the spectrum representation again of x of t then is here. For instance, here, guys, it's 1/2, let's say, for A0. I have k equals 1, right? For instance, which is 25 hertz actually, k equals 1. And then 50 is k equals 2. Actually, I already know it's 0 at the even harmonics. So 50, okay, let's maybe write. So it's multiples of the f0. This is f0. So always try to find f0 in the plot, right? In the spectrum in your mind. F0 is there and there are multiples of it. I already know these are 0. 100, 150, right? 125. Why? Because K3, K4, K5, K6, you see the even ones are always 0. So let's maybe start writing the odd ones. 1/pi, k equals 1, just use this formula. This is AK for k odd. Okay? This is what we're using. K equals 1 is 1/pi. So let's just draw 1/pi, and I should try to put e to the minus j pi over 2 here. And I know this was a real signal, so it's gonna be complex conjugates here. So it's really 1/pi. Also, you can do it from the math here. Insert k equals -1, that's gonna bring you to the same place, which is same coefficient here, a -1. So these are really, guys, by the way, A1 and A -1. And this is important, F0, and this is k equals -1. The same thing on the right, left-hand side. -50, -75, and it goes on like this, of course. I mean, it's like till wherever I can go. Let's go a little bit more. It's fine. So let's fill in a little bit more. This is A2 is 0 and A -2 is 0. So this is A2, 0. This was A0 already, which is nice. A -2 is 0. Okay. So now continue with A3. A3 is 1/3 pi. 1/3 pi times, again, actually it's always the phase is there, right? The phase shift is there, minus pi/2. Okay. And here I have its complex conjugate. You guys see, this is really writing the signal as sums of cosines and sines. I mean, depending on phase shift, it could be sine, but sums of cosines. I will show in the plots now, just soon. Plus, right? Now plus pi/2. And guys, it's gonna be going like this, 1/5 pi. It is 0 here. This was A3. This is A3. This is A -3. A4 is 0. A -4 was 0. Now A5 is 1/5 pi. Just apply the formula e to the pi/2. 1/5 pi e to the j pi/2. So you can see this is really, this has this form. I mean, it's a discrete spectrum. You should also realize this is a discrete spectrum. For periodic signals, we have discrete spectrum, meaning we just have values of the spectrum at multiples of the fundamental frequency. This is important. Just has values at kf0. This is why I also say it's a discrete one, and it's a very compact representation. Okay, so from here now we can start synthesizing x of t. For instance, if you just can really, we are finite creatures, right? I mean, we can't really do infinite sums. So we typically take, for instance, this capital and very large. So what we do is take the AKs from here. I know my basis functions, 2 pi k, 25t. So start synthesizing the signal. So for instance, x sub n is a approximation to the signal. As by the way, the goal is, guys, as xn, so maybe I should say the goal is, maybe let's do this in the next slide. The goal is we try to make the error we make with this approximation, x sub n t is this x of t or x. Yeah, let's first write it's an absolute value, but it's the same thing anyway. This guy should go to 0 as this capital N goes to infinity. That's the idea. Okay. This is valid, by the way, guys, valid for a continuous signal. I mean, this error goes to 0 as N goes to infinity. I mean, as I increase the number of coefficients I have for a continuous signal. But for a discontinuous signal, there is always an error remaining. Due to those discontinuities, they cannot be really represented well. This max, let's call this error E and T, E sub n t. You see the error we make with this approximation of x sub n t. This was, maybe I should say, yeah, actually it's defined in this way. Okay. Max E and T does not go to 0 for a discontinuous signal. Actually, this doesn't work. But for a discontinuous signal, this guy goes to 0. This max, I should say, max of this. Okay? E max, worst case error. So this is really like a worst case error. Okay? So we should say this E and T, but for a continuous signal, this is nice. Max E sub n t goes to 0 as n goes to infinity. Continuous. This is very important to know. So then these errors, guys, this is called Gibbs. This leads to something called a Gibbs phenomenon. This is visible at, I will show you the plots now. This is visible at discontinuities of the signal, meaning the approximation cannot really get close to the signal, discontinuities of the signal. So look at the waveform. Our waveform was a square wave. It has really many discontinuities, right? I mean, in a period, it has at least, in one period, it has like at least 3 discontinuities, right? Goes down, up here, goes down. I mean, depends on where, if you include the boundaries, it's 4 discontinuities. Okay, this is called Gibbs phenomena. For instance, if I had I will show triangular visible at discontinuities of the signal, e.g., check the square waveform. Okay, but if we had, for instance, e.g., for a triangular waveform, triangular signal or waveform, you can, sometimes it's called a waveform. For instance, if I had this signal, periodic, triangular periodic, always we should say this. First, if I had the same thing, but in this way, guys, this is a triangular signal. At least it's continuous, right? It may not be differentiable, but it's continuous. So do the same thing with 0 point. You see, I just converted the same signal with the same period to a triangular waveform. You can look at, so again, T0 is 0.04, F0 is 25 Hertz. Okay. Fourier series coefficients, actually, maybe Yeah, but it would take too much of our class time now. It could be an exercise for you. But what is A0, for instance? You guys can tell me coefficients. For instance, A0 is already 1 over T0, right? And the area underneath, so that would be really 0.02, which is really again 1 over 2, right? It's correct, right, guys? Okay, and Fourier's other AKs, they will be proportional to 1 over k square for odd k this time. So guys, this was decaying with 1 over k. So square wave had, actually, you see the spectrum had this form, k, AKs. Of course, it was discrete, but this form, waveform, or this pattern decays with, remember, 1 over k. Why? I mean, just look at the form of the signal here, 1 over k. If you view this as a function of k. Here, triangular way, you see decays faster for odd k. So, I mean, you can derive this, but you see decays faster than the AKs of square wave, which is good actually. If it decays faster, so this means actually, guys, this is another example. Now, if we were to draw the AKs, here K, that would mean it would really have, so for instance, A0 is 1 over 2. Again, cancel, all right. A0 was 1 over 2. And then we will have odd case, right, this time. And then we also had odd case here though, right? Also exactly, we had odd case here. K odd decays with 1 over k, k odd. We had this case for a case in this case. But now it's decays with 1 over k square. So it will be like, I mean, sorry, A1 here, and if k equals 1, of course, then k equals 3, k equals 5. You see, it's going to be really, then this is A3, A5. You see what I'm doing, right? This is A minus 1, A minus 3, A minus 5, and like this. So that would mean decay faster means it is good for us. There is less error at the, as we go towards the infinity. Okay, so here is the spectrum. This was the spectrum. So let me draw this waveform. Just, I mean, but guys, it's the discrete waveform. Of course, I'm just drawing the envelope. Okay, that is the, here also, maybe just for your better visualization, I draw this is the envelope, meaning really I'm joining the lines between the here form of the signal, the envelope of spectrum, I mean, here. Okay. So let's maybe look at some slides to see nice visualizations of these. So questions? Yes, the area is 0.04 times 1 over 2. That's why I wrote 1 over 2, which is fine. Okay? Yes, I added 1 over 2, Sani. So guys, let's check the slides here. I'm trying to see. Let me share it from, maybe I can try to share them from my tablet, guys. Some Fourier series examples. Okay, here, let's just do this. Guys, let's see. No, this is not it. Here. It's trying to open. If not, I'll open it from the desktop or I mean the laptop. Okay, I can just open it from the desktop. I can't open. All right, something is wrong. Let's share it here, guys. Let's look at some examples. Here, let me see. What was it? Some examples. These slides are, by the way, the textbook slides. You have access to these. Yusuf, Fırat, you guys, Yusuf, you are here, I think. Please share them the link.
Okay.
It's on the textbook website, DSP first.
Should I share the link for all the
Yes,
slides?
announcement maybe. Yeah, maybe make an announcement with the link.
Okay, hocam.
Yeah. And also we can put which slides are now valid for each week. But actually they can find from the chapters. We should say which chapters are included.
Okay, hocam.
Okay, thanks. So guys, let's see. We've done already. We derived the Fourier series coefficients. A harmonic signal is periodic. We said this last time. If I sum harmonic complex exponentials, I get a periodic signal. Okay. Actually, now I believe we should also touch upon that point. Yeah, maybe you could be like, what could be a non-harmonic signal? Let's also do that, guys. I think it's also important. I want to give that example before going to these slides in the tablet, because I think that's one thing that's just we left out. So for instance, guys, I can ask you this example. X of t is sine 2 pi square root 2t plus, let's say, 2 sine 2 pi 4t. And you can't see it, right? Interesting. Let me reopen it. I wrote something here, but it's all black. I'm seeing an all black screen. It's there. Okay, so I wrote a signal, an example signal, guys. So I'm asking you, is there a Fourier series representation of this signal? Because we know of question, can you find a Fourier series representation? I question to you, represent Fourier series. I mean, you can always show the frequencies in a spectrum, by the way. The spectrum is not equivalent to Fourier series, but what are the frequencies in this signal? You just have to say, hey, I see these two frequencies. There is an F1, which is square root 2 Hertz. There is an F2, which is 4 Hertz, right? But is there a greatest common divisor of these? Of course, there is none. So there is no F0, right? No fundamental frequency. So this is really, when you add these two sign components that are really not harmonically related, it's not a periodic signal, guys. This is not so this is important. This is not a periodic signal. Therefore, no Fourier series representation. This is important. Maybe I can show, is it here? Yeah, for instance, this was actually, by the way, Fourier series representation of the triangular wave. Here, important thing is, first look at X3. I mean, it's not non-harmonic. I should open a non-harmonic version here, but anyways. So it's a little bit jumping now, but remember the X sub n? This is 3, when n is 3. So you see, I added 3 harmonics to represent this triangular signal. This is another triangular signal. It's already those signs when added, first 3 harmonics, when added, they are already coming close to a triangular wave. X5, 5, add 5 of them, gets better. And X59, look guys, when n is 59, it's really a very good approximation of a triangular waveform. So because we said it's a continuous signal, triangular waves, its Fourier series coefficients or representation, spectrum decays with 1 over k square, which really fast is a fast decay. So for large n or large k actually, we have then AKs are becoming 0. So very large, this would mean, seeing this, very large AKs are almost 0. So I really have a good representation, but this won't be the case for square wave. I think I want to, probably I'll have to show them somewhere else, but I will also show you the this spectrum of this guy. But you see this, right? What I'm saying here. These are not harmonically related. I mean, there is, of course, an irrational number here, guys. An irrational number, a frequency is an irrational number. There is no greatest common divisor, no greatest common divisor, let's write, of these two, of F1 and F2. That's why we ended up with no fundamental frequency, sorry. So let's now, this is important. This is a not periodic signal. This is important, not aperiodic. Let's see, this was important, non-periodic. This was the keyword here. Non-periodic signal, X of t. Okay? So now let's go to the slides. I think I should have, from before, guys, this is also in the slides, but I have saved this separately just to show this is important. Harmonic, this is, for instance, just look at, I wanted to open it up in my tablet, but now it's on the laptop, so I won't be able to write, but you see my mouse, right? So look at this frequency here. I see a 20 pi, so 10 hertz, right? I see a 30 hertz and 50 hertz. Fundamental frequency, as I wrote here, is 10 hertz, right? Because this signal is, X of t is combination of 3 sinusoids, right? And they are all multiples of 10 hertz. And I'm expecting this fundamental period of 0.1 seconds, t is 0.1. So this plot shows sum of cosine waves with harmonic frequencies, okay? It's just continuing, just like trying to say it's 3 lines, but it's just continuing the same thing because it's an infinitely long signal, right? So this is, I think, showing us when we add 3 harmonically related periodic signals, we get another periodic signal. Here, the added signal, its fundamental frequency is, of course, 10 hertz. It's X of t. And we can see that period here, actually. So t is 0.1. Just check between two, guys, between 2 peaks here to here, for instance. Let me see. Or the center point from here, start here, to center point here. This is not labeled in the graph, but it's 0.1 seconds here. So it's 1 period. I can see that's coming from this main component. I can also see these higher frequencies. So that's the low frequency. And we added 2 higher frequency signals, 30 hertz and 50 hertz on top of it, okay? No, fundamental frequency is 10 hertz, but it's 25 radians per second. They are equivalent, radian frequency, remember? We can mention it in 2 ways. So you should say 20 pi radians per second. which is equal to divided by 2 pi, it's 10 hertz, okay? So now look at, guys, just change. Remember, this is 20 pi, 25 pi times 3. This is actually square root of 9, right? These two will remain the same, first and third components. The middle one, this was square root of 9, 3, but now make it square root of 8. So a little bit change in that frequency, but so slightly disturbed. That first one was x1t. Now I have another signal, but you see, guys, try to find a period. You can't. This is sum of cosine waves with non-harmonic frequencies. You can't say here, is there a fundamental period? No, right? This was also changed a little bit. I thought this was kept the same. This was 5 here. So root square root 25. Now it's made square root 27. Look at the result. Is it periodic? You may think it's somehow, but you won't ever find, guys, here the same pattern repeating itself. I mean, sometimes we call nearly periodic signals quasi-periodic, but here I don't believe it's even like that. I'm trying to see. For instance, this one looks like this, but then the next waveform to it, they are all very different. I mean, this guy and this guy. So it's really not periodic. This is a non-harmonic signal. Is it clear? So you see that finding that fundamental frequency and finding its multiples in the frequency components of the signal just tells us the overall signal when added together, it's also periodic. If we can't find it, it's not periodic, okay? So the spectrum, let's look at the spectrum here. This is spectrum of X1, the periodic one. You see we have components. We have a special relationship to get a periodic signal. We have at 10 hertz A1, let's say. You can also find the coefficients, of course. A1, A3, and A5 of and 1 minus 1 over 3 and 1 over 5, right? We divide by 2, remember, because these are cosines from the Euler formula. Of course, this minus 1 over 3 minus 1 could go as e to the j pi, but it's fine. It stayed as minus here. This was the case, like multiples. These discrete spectrum samples were at multiples of the fundamental frequency, but now spectrum of x of t does not have a fundamental frequency. It's not periodic, but I can still show the spectrum. That's the important point, guys. I mean, it said irrational spectrum, but we could say non-periodic signal spectrum. I think that could be a better title for this one. So you could look at a spectrum then, spectrum representation like this, and say whether the signal, tell whether the signal is periodic or not. For the first time, you could locate 10, and then you could find the other component at its multiples. But for the second one, you would be like, hey, there is 10, but there is 20 square root 2, 30 square root 3. I mean, 30 square, yeah, square root 3. These are not really multiples of each other. So this spectrum in the bottom does not correspond to a periodic signal. This is also important. It's good we covered that. Okay. So, okay. So I noted for you here in the notes, look at the slides. So now let's continue. This was good. Let me see what this was. Okay, this was another example. For instance, rectified sine wave, half wave rectified sine wave. This is really all mathematical manipulation. This was given to you. Then you would really find the fundamental periods. It's T0 here given as symbolic. It could be numerical. The question was compute A1, A minus 1, and A0. Please do this as an exercise. And then if we can share this slide set or these 2 slides with you, you just have to bring the sign here, but it's rectified, meaning the negative parts are erased, suppressed to 0. So it's just you see non-zero in the half of the period. 0 to t0 over 2. You use your Euler formula. Okay, do the math. It was a little bit here more manipulations, require more manipulations, but in the end you end up with, you see, for k odd it was 0, for k plus minus 1 it was special case, and then but I mean this should let me see, for k even, okay, it is 1 over k square. Yeah, it's a k plus minus 1 has to be done as a special case. Try to do it, we can share it with you. I want to show now for the square wave, that was my goal here. After that we go to the quiz, guys. Spectrum. Here actually full rectified sinusoid was solved, by the way. So this is the first plot is the sinusoid. This was just absolute value taken, and full rectified means just take the negatives to the positive. Halfway rectified means just kill the negative parts, right? Phillips the negative lobes. So it's really this signal that you are working on. You can do the math, okay, and come up with a case like this. Again, you see 1 over k square type decay. You can then actually reconstruct the signal, start reconstructing the signal. For instance, sum of DC first and fourth harmonics. Let me see, this had a DC component, yes. It doesn't have a zero integral, it has non-zero integral, so it has an A0 coefficient. Yes, A0 is non-zero here. Now you start adding, actually, let me see. I mean, this is just to show that A0, but just discard that for a moment. You start added, even if you added first to fourth harmonics, you started to get something like that, the rectified sine wave. Sum of first to 9 harmonic, it's much better. You see the point? So guys, this is really, in a way, this summary of what we've done. We say we take a signal x of t. Maybe I can actually make this. Take a signal x of t. We do a Fourier analysis, meaning we extract these harmonically related sinusoids, right? Through our Fourier analysis integral, AKs are calculated. Let's say this was x of t given this rectified sine wave, full rectified sine wave. You have to define your k f0, little f0 from the fundamental period. Then go to, in the middle, go to the spectrum plot. Here, for instance, it was, you see the envelope is a 1 over k square 2 decay. I can compactly see, you see, immediately see which components are there. This is just an illustration, A0 to A7. But the important point is this is a discrete spectrum, and I just have samples at multiples of F0. Some of them could be 0, of course. Like, for instance, even K was 0 in some of the examples we've seen. Then, for instance, from here, we can say I will be approximating this signal by just 7 harmonics or 9 harmonics. Then we approximate the signal. Take the n number of coefficients. This is also compression, actually. I don't want to represent it by infinitely many signal points or coefficients. I just have capital N of them and add them up and obtain such an approximation. You see, this is an approximation to the original signal. Yeah, let's look at this one and maybe, or let me see. Okay, it's 15. I think you would need 15 minutes for the quiz, right, Yusuf?
Yes, hocam, I think 15 is enough.
Okay, 15. So let me leave now. We can next time look at, it would be a recap also, which is good. We can recap this continuous time Fourier series next time. We will go to discrete time signals and discrete time Fourier series, okay? So there will be discrete time like digital frequency, some sampling, we start sampling a little bit. So please study what we did until now, okay? So I think we can leave it, Yusuf. Yeah, I will make you host.
Yes.
Hocam ben bir süre
Arif Bey.
dinleyemedim de bu slaytlar sisteme yüklenecek mi acaba?
We will give the slides links. This is not our slides. This is the textbook slides. Thanks for asking. We mentioned it, but probably you didn't hear. Yusuf will share the links to DSP first or SP first. The authors have two versions of the book. You can take a look either at the, of those. Yusuf, yeah, after today lecture, can you share the slide links so they can download and start looking, and tell them which chapters? Now, guys, look at slides for chapter 2 and chapter 3, okay?
Yes, hocam, I will publish an announcement. By the way, do you want another announcement for the previous slides, for previous lectures?
You can do it in one announcement.
One announcement, okay.
Yeah, because previous chapter was chapter 2, spectrum representation. Now it's Fourier series. You can point to the correct set of slides. Okay, so I will pause the recording. We'll see you.